Imagine building a rocket engine one atom at a time, a concept so intriguing that even Elon Musk marveled at it. This isn't science fiction, it's the reality of electroplating, a fundamental electrochemical process first discovered in 1805 by Italian chemist Luigi Brugnatelli, who used a voltaic pile, early battery, to deposit gold onto a silver surface. Electroplating literally uses electricity to deposit metal ions as solid metal, atom by atom, onto objects, forming a smooth, tightly bonded coating. Over the past 2 centuries, this atomic-scale manufacturing technique has exploded in use, from gilding jewelry and cutlery to chrome plating car bumpers, and is now driving innovations in electronics, aerospace, and even rocket engineering. Each deposited atomic layer can drastically enhance an object's properties, making it more conductive, more durable, or corrosion-proof. In this video, we'll dive into how industries harness electroplating to revolutionize manufacturing, from automobiles to SpaceX's rockets, blending first-principle science with real-world industrial feats to inspire both entrepreneurs and future scientists. Electroplating is essentially 3D printing with atoms via chemistry. The setup is straightforward. A metal source dissolved into a solution as positively charged metal ion migrate under an electric current and get reduced, gain electrons, at the cathode, the object we want to plate. Each ion that arrives and gains electrons becomes a neutral metal atom, attaching to the surface in a crystalline layer. By controlling the current and time, manufacturers can dictate exactly how many atoms deposit. Faraday's law quantifies this with precision, linking electric charge to the moles of metal plated. For example, depositing 1 mole, about 6.02 times 10 to the 23rd atoms, of copper or nickel requires about 193,000 coulombs of charge due to the ion charge. In practice, that means a high-capacity plating setup driving 400 amps can lay down on the order of 4.5 times 10 to the 24 metal atoms per hour, about 1.25 times 10 to the 21 atoms every second. So while the process is 1 atom at a time, it's happening literally millions of atoms per femtosecond under industrial conditions. This atomic precision gives electroplating unrivaled control. Layer thickness can be nanometers or centimeters as needed, and complex shapes can be uniformly coated even into recesses. The metal coating grows uniformly, filling in microscopic crevices and even self-leveling with the help of proprietary additives that refine grain structure. Modern platers often use special brighteners, levelers, and agitation techniques to ensure a dense, deft-free deposit at faster rates. The result is a metallurgist's dream, a part that can be vastly improved by a tailor-made skin of another metal, bonded at the atomic level. Electroplating, the electrically driven atomic fabrication of metal, has proven its power everywhere, from SpaceX's early Merlin rocket chambers, where thick nickel shells were grown over grooved copper liners to create seamless, coolant-filled walls, to IBM's nanometer-scale copper interconnects that unlocked faster microprocessors. Though plating's femtometer-thick rocket jackets can take days and suffer impurity or stress limits, prompting a shift to HIP bonding and 3D printing, its precision remains rivaled. Satellites still rely on gold-plated waveguides, automobiles on zinc or chrome anti-corrosion skins, and MEM systems on Liga-plated microgears with 100:1 aspect ratios. Modern electronics depend on gold-plated contacts and void-free superfilled copper vias, while nanotechnology exploits electro-deposited nanowires grown in templates. Research now pushes ultra-high-speed jet plating, pulse reverse waveforms that create nano-twinned copper, ionic liquid baths that finally plate aluminum and titanium, and hybrid 3D print electroform methods that turn plastic lattices into solid metal. Composite coatings embed diamond or PTFE for wear or low-friction surfaces. Trivalent chromium replaces toxic hexchrome, and AI-controlled baths slash waste. From jewelry that wears atomic-thin gold to rocket nozzles that once grew atom by atom, electroplating's ability to tailor metals at any scale, and ever greener, faster, smarter, keeps it a cornerstone of manufacturing innovation.